I did a project to design a life support systems for manned spaceflight. And the idea was to get my solutions from nature. So try to do what we call biomimicry. So this was a project I did for my thesis, my master thesis. And to start with, I'll quickly talk about what is biomimicry. So it is the art of taking the solutions for a certain problem from nature. So it happens to be an Italian guy, so I'll start with Leonardo da Vinci's quote, who said that those who are inspired by a model other than nature, masters of all masters, are laboring in vain. And I think this is a good start for my presentation because I will tell you how biomimicry is the key, one of the keys that we have to harness if we want to also improve our understanding of space and how we can get there. So one of the problems is that we're humans. So we are really linked to our planet. We need air to breathe. We need to get protected by our atmosphere, our magnetosphere. That protects us from many things. I will talk about them later. We need food. Obviously, we don't find food in space. We need to process that food and then to go to the toilets. And obviously, we cannot go to the toilets in space, or at least it's very difficult. And I think one of the hardest problems is water. Water is key to sustain life in space. So our dear planet is a protection for us. There are two main protections. So one is called the atmosphere, which protects us against some small objects that can fall by burning them, so what we call the shooting stars. But we also have the magnetosphere, and I think we talked about it yesterday, which protects us against radiation. Radiation is one of the hardest, like the biggest hurdle for manned exploration. If we want to go to Mars, send humans there, we need to find a solution for radiation. So what is radiation? Radiation, to really go quickly to it, it has two main sources. So there are what we call the cosmic galactic rays, GCR, which really comes from further sources from the cosmos. And the other source is the sun. The sun is producing a lot of rays that can be very, very harmful for astronauts. These are what we call the solar flares. They happen every 11 years, approximately. And you shouldn't be in space when that happens because it gives you cancer in 2 seconds. So I won't dwell into the physics of it. But roughly, what can we do to protect ourselves against radiation? There is this very simple equation that I put there on this slide. If we want to increase the shielding, we can either limit the time we spend in space, so the time you are facing the radiation, or you can increase the shielding. So if you have a better shield, then you are more protected against radiation. It's very easy. So talking about this part, because obviously if we want to spend less time in space, we need to have a better propulsion systems. So instead of going to Mars, for instance, that would take 200 days or 200 or 300 days, you need to take a week, and obviously we cannot do that now. But the remaining solution that we have is shielding. We have to really solve the shielding part. The shielding works as you put a material between the astronaut, and the source. And you can either increase the thickness of that shield, or you can work on the materials. So if you have different materials, they can protect you better than others. And there are different rays, different kinds of rays. The most dangerous are the gamma rays. These are the most powerful ones, and it's very, very hard. And our magnetosphere protects us against gamma rays. X-rays are the ones that when you go to an airport, they check your luggage and stuff. This is what they use, or to the doctor. And another problem that we face also when you go to space is waste management. Obviously, when you go to the toilets, you have gravity, you have lots of space for storage, so you have lots of complex mechanisms that just take care of everything. You don't have to do anything. But in space, this doesn't exist. So we don't have gravity, and we lack space. So we need to really process everything. All the waste that is produced in space needs to be treated. So yeah, many problems. So I'll quickly sum it up here. Radiations, the waste that produces, and the efficiency if you want to go to space, you have to really calculate the mass that you're taking with you. So you cannot take 8 tons of water or 9 tons of water to Mars. You need to recycle. So on the ISS right now, when I did my thesis, it was 70% of the waste that is produced of the urine is recycled, and that is not enough. We need to close the loop, the water loop. So everything that you just take, you need to take it again. So recycle and close that loop. So what if I could tell you that some solutions for this problem exist in you? You have the solutions we have the solutions in our bodies. Quickly, 3 images right here. On the upper and left, you have a molecule that we call melanin. So that's a molecule that protects us against UV light. So when you go to the beach, you just put some sunscreen that's inspired from melanin. On the right hand, you have what we call the kidney. So that's what processes what you take and then filtrates through the body. And then we have the large intestine. So there are 3 main principles behind these 3 tools. In the melanin, there is a pigment. So there was a research that was done in 2013, 2014 that said that there was an algae that could thrive in nuclear reactors. So you heard of Fukushima? So everything, like all life around that place died. Like it was very hard for life to sustain, except one algae. And that algae, they found that it was developing a molecule, which is called melanin nanoshells, that could protect it against radiation. So yeah, they just found that this algae was protecting itself using melanin. So the researchers tried to use that to find solutions against cancer. So I said, why not try to use this system, but for space? Try to use melanin and use it as a shield, because it apparently can protect you better for radiation. Then on the kidney, you have a phenomenon called osmosis. So osmosis is a natural phenomenon that equilibrates the concentrations. So it's a filter. Let's call it like that. It's a filter. And the large intestine has also another phenomenon called peristalsis. It is a natural way of displacement. And it's just, how it squeezes what you eat and just make it displaces it. So I said, I will try and combine all these principles in one system. This is so this is my proposal. This was my proposal. It is a life support system. It's a brick. It's a small module that includes 2 parts. So on the upper side, you have what is supposed to simulate the kidney. So you have liquid wastewater, so urine, that goes inside a tube. So these are 2 concentrical tubes. The urine goes inside, and you have some very thin layer that has very tiny pores that does the osmosis. So you put a drawing agent, which is salted water, for instance, or you can put anything else that would just take water out of urine and just leave the dried components inside, so the yellow part. So this way you can recycle. That is exactly what they use on the ISS. But I just took it again and make it more functional. But if you can ask me questions later, because I try to also use that as a heat shield. But anyway, what you have to retain is in the upper part, the water recycling. Then on the lower part, you have solid waste, and I simulate the large intestine, so it has peristalsis systems. What you can see in these blue and red circles, these are some actuators that would squeeze and make the waste displaced. And obviously you would get cold and humid air on one side and also get water out of solid waste. The main objective of this system is, on one side, to get as much water as possible from the waste. And second, you can use the waste to produce melanin. So you remember melanin, this pigment that was in this algae that I told you about? So we could coat the system with melanin in order to increase radiation. And it happens that one of the best radiation shielding materials is water. Water is very, very good against radiation. So this system contains a lot of water. Then you can use this water to produce melanin. So I said this could be a very good radiation shield. So this is the concept. It is a module that you can connect together and circle around the spacecraft. So this would give you space for your waste, so you can contain your waste. This could recycle the water that's inside your waste, the waste that is produced by the astronauts. And on the same time, you could produce melanin to give you more radiation shielding. So it does 3 things on the same time. And I made it modular, so a lot of small components that you can plug together for 2 reasons. I think I explained it like, yep. So I'll go forward and then come backward. One thing that we know about GCR, so galactic cosmic rays and solar flares, galactic cosmic flares come from all directions. So they come from the cosmos, and the professor just before me said it. It's very isotropic, so they come from all over the universe. Whereas solar flares come from the sun, so it has one direction. So if it happens that you are in space when there is a solar flare, which I don't wish you just unplug all the systems and put it in one direction, because you have a couple of days to know where they come from. And if you're just going to Mars and there's no problem, you just put it uniformly around your spacecraft. So this was the concept. And I said I wanted during my thesis, because I only had 7 or 8 months to work on this, I wanted to design a small prototype to simulate the peristaltic movement. So the peristaltic movement is induced in my prototype, so it's the image that I put there, by some actuators that would push the tube in order to create a displacement, so that you don't have to touch what's inside the tubes. So in order to simulate the waste, I took some laundry stuff and put it inside. And I think I have a video to show you how it works. Okay. So you can see here, the actuators would just push the tubes, and then the liquid inside, which is very viscous. So I made it as viscous as possible, so that gravity doesn't help. And then the system would just make the waste move inside. Up. Where is my presentation? Okay, I'll just do this. So this way I show that peristaltic movements could be used also in space. On the ISS now, there is a peristaltic pump, but it's a circular peristaltic pump, something that really exists. But this has never been done in space. So I also propose that as something to be further assessed for space. And obviously this movement works. It works on the ground. Now it would be good to test it in space. So as explained, there are obviously many more steps to, this is a concept, obviously. It's really the baby steps of a project. And there are many studies that need to be done. During my thesis, I also studied some parts related to radiation, so I did some simulations. So feel free to ask me some questions after if you have them, and I think I will close it with that. Thank you. So feel free to ask if you have any questions. Yes? How pure would the water be when it comes out from your system? Well, my system would not be the only system that's in the process. It would be the first part of a long architecture. So you would get water, but it's not drinkable, obviously. So you need many other processes, and these processes are, I would say, not simple, but they're known, that you can do them. I don't know if, yep. This is, the second picture is on the ISS right now. It's called the water recovery processor. And basically, this would come after my system. So you'd have this, and then this would do all the stuff to mineralize it and get it drinkable again. Grazie mille.